Earth is called the water planet. We're covered in oceans. 70% of our surface is blue. But here's what scientists just discovered. Earth has barely any water compared to other worlds in our solar system. Europa, one of Jupiter's moons, has twice as much water as all of Earth's oceans combined, and it's smaller than our moon. Enceladus, a tiny moon of Saturn, shoots geysers of water hundreds of miles into space. Even Mars, the dead desert planet, used to have more water on its surface than Earth has right now. We're not the water world. We're the exception. If you're ready to see how Earth's water compares to the hidden oceans across our solar system, hit that subscribe button. The truth starts now. Let's start with a fact that sounds impossible. If you took all of Earth's water, every ocean, every lake, every glacier, every drop in the atmosphere, and compressed it into a sphere, that sphere would be 860 miles across. That's it. A ball smaller than the distance from New York to Chicago. Sitting next to Earth, which is almost 8,000 miles wide, it looks pathetic, like a marble next to a basketball. Here's the breakdown. Earth's oceans hold about 326 million cubic miles of water. Sounds massive, but Earth's total volume is 260 billion cubic miles. Water makes up just 0.12% of our planet's volume, 1/10 of 1%. We're not a water world. We're a rocky planet with a thin coating of water on the surface. And most of that water is useless to us. 97% is salt water. Of the remaining 3%, 2/3 is locked in ice caps and glaciers. Less than 1% of Earth's water is fresh, liquid, and accessible. The amount of water humans can actually use would fit in a sphere 35 miles across, smaller than some asteroids. But here's what blew scientists' minds when they started exploring the solar system. Other worlds have more, way more, and it's not even close. Europa, a moon of Jupiter, is 1,900 miles in diameter, about the size of Earth's moon. Its surface is frozen solid, temperatures hovering around -260 degrees Fahrenheit. But underneath that ice is an ocean, a global ocean. Liquid water surrounding the entire moon. Scientists estimate it's 40 to 100 miles deep. Earth's deepest ocean, the Mariana Trench, is 7 miles deep. Europa's ocean is more than 10 times deeper. And because Europa is completely covered, with no continents breaking the surface, the total volume of water is staggering, twice Earth's oceans, maybe 3, all hidden under a shell of ice. And Europa isn't alone. Ganymede, Jupiter's largest moon, also has a subsurface ocean. So does Callisto. That's 3 moons around Jupiter, each containing more water than Earth. Saturn has Enceladus, a moon only 300 miles wide, smaller than Texas. Yet it has a liquid ocean beneath its icy crust. We know because the moon shoots geysers through cracks in the ice, plumes of water vapor launching into space visible from 500 million miles away. NASA's Cassini spacecraft flew through those plumes, tasted the water, found organic molecules, salt, everything you'd need for life. Then there's Titan, Saturn's largest moon, bigger than Mercury. It has lakes, rivers, rain, an entire hydrological cycle, except it's not water. It's liquid methane and ethane, hydrocarbon seas at -290 degrees. But beneath Titan's surface, another ocean, liquid water mixed with ammonia, stretching miles deep. More water than Earth, hidden under a frozen crust and a thick atmosphere of nitrogen. Scientists have counted at least 10 worlds in our solar system with more liquid water than Earth. 10! And we haven't even left the solar system. We haven't checked the moons of Uranus or Neptune up close. We haven't explored the thousands of exoplanets orbiting other stars. If water is this common in our tiny corner of the galaxy, how much is out there in the universe? And if Earth has so little, why do we exist at all? Here's the mystery that keeps planetary scientists awake at night. Earth should have more water. Models of planetary formation predict we should be soaking wet. Our location in the solar system, the materials that built us, the bombardment history from comets and asteroids, everything points to Earth being a water world. But we're not. So where did it go? Theory 1. Earth lost water during formation. When our planet was young, about 4.5 billion years ago, it was a ball of molten rock. Surface temperatures exceeded 2,000 degrees Fahrenheit. Any water that existed would have boiled off into space. Hydrogen and oxygen escaping into the vacuum, stripped away by solar wind before Earth cooled enough to hold an atmosphere. This makes sense, except it doesn't explain where the water we do have came from. If Earth lost its original water, something had to bring it back. Theory 2. Comets delivered water. Comets are dirty snowballs, ice mixed with rock left over from the solar system's formation. Billions of them exist in the outer solar system, and occasionally they get knocked inward, crashing into planets. Earth was bombarded by comets for hundreds of millions of years during a period called the Late Heavy Bombardment. Each impact delivered water. Millions of comets over millions of years, filling the oceans drop by drop. Great theory. Except when scientists analyzed the water in comets, the isotope ratio didn't match Earth's water. Comet water has too much deuterium, a heavy isotope of hydrogen. Earth's water is lighter. Different source. Theory 3. Asteroids brought water. Not comets, asteroids. Specifically, a type called carbonaceous chondrites. These are rocky asteroids from the outer asteroid belt, and they contain up to 20% water by weight. Locked in minerals, hydrated. When these asteroids slammed into early Earth, the impacts released that water. And when scientists tested samples from carbonaceous chondrites, the isotope ratios matched. This is probably where Earth's water came from. Asteroids, rocks, not icy comets. Rocks carrying water in their minerals, delivering it piece by piece over hundreds of millions of years. But here's the problem. If asteroids delivered our water, why didn't they deliver more? Other worlds got drenched. Europa, Enceladus, Ganymede. These moons are smaller than Earth, yet they have oceans that dwarf ours. What made Earth different? One possibility? Location. Earth formed in the inner solar system where temperatures were higher. Water ice couldn't exist. By the time Earth cooled enough to hold water, most of the water-rich material had already been swept up by Jupiter and Saturn. Those giant planets acted like vacuum cleaners, capturing icy bodies before they could reach the inner planets. Mars got some, Earth got some, but the outer moons got the rest. They're sitting in a region where water ice is stable, where every collision adds to the reservoir instead of boiling it away. Another possibility? Earth lost water to space. Not during formation, after, for billions of years. Our planet sits close to the sun. Solar radiation heats the upper atmosphere, giving molecules enough energy to escape. Hydrogen, being light, escapes easily. Oxygen gets left behind, reacting with surface rocks, getting buried in the crust. Slowly, over billions of years, Earth bleeds water into space. Not fast enough to notice in a human lifetime, but over geologic time, significant. Some scientists estimate Earth has lost an ocean's worth of water this way. Maybe more. Mars definitely lost its water this way. Mars used to have oceans, rivers, lakes. Evidence is everywhere. Dried up riverbeds, ancient shorelines, lake beds filled with sediment. Mars was wet, warm, maybe even habitable. Then it lost its magnetic field. Without that protective shield, solar winds stripped away the atmosphere. Water evaporated, hydrogen escaped to space. Oxygen bonded with iron in the rocks, rusting the entire planet. That's why Mars is red. It's oxidized. The remnants of a lost ocean locked in the dirt. Earth kept its magnetic field, kept its atmosphere, kept most of its water, but not all. We're still losing it. Every second, 3 kilograms of hydrogen escape to space. Doesn't sound like much, but multiply that by billions of years and it adds up. We're a dying water world, just dying slower than Mars. Let's talk about the places that make Earth look like a desert. The real water worlds. The moons scientists are now targeting in the search for life. Because if water equals life, these are the places to look. Europa is the crown jewel, Jupiter's fourth largest moon. From a distance, it looks like a cracked eggshell. The surface is pure ice, bright white, reflecting sunlight like a mirror. But those cracks tell a story. Tidal forces from Jupiter flex Europa's interior, heating it through friction. That heat melts the ice from below, creating a liquid ocean. The ice crust floats on top, constantly breaking and refreezing as the moon flexes. Scientists estimate the ocean is 40 to 100 miles deep, maybe deeper. It contains more water than all of Earth's oceans combined, and it might be warm enough for life. NASA is planning a mission, Europa Clipper, launching in 2024, arriving in the 2030s. It'll fly by Europa dozens of times, using radar to peer through the ice, mapping the ocean below, looking for plumes, analyzing chemistry, searching for signs of life. If life exists anywhere in the solar system besides Earth, Europa is the top candidate. Then there's Enceladus, tiny, only 300 miles wide. You could fit it inside Texas. But this little moon is active. Geysers at the South Pole shoot water into space. Cassini flew through those plumes and found everything: water vapor, ice crystals, salt, organic molecules, including methane, which can be a biosignature. The ocean under Enceladus is in direct contact with a rocky core, meaning hydrothermal vents, underwater volcanoes, just like the ones on Earth's ocean floor that support entire ecosystems without sunlight. If life can exist around Earth's hydrothermal vents, it can exist on Enceladus. Ganymede is even more impressive. Jupiter's largest moon, bigger than Mercury. It has a magnetic field, the only moon in the solar system with one. And beneath its icy surface, a layered ocean. Not one ocean, multiple layers. Ice, water, stacked like a cake, because the pressure at different depths creates different forms of ice. Some scientists think the deepest layer might be hundreds of miles down, warm enough for chemistry, complex enough for life. Titan is the wild card. It's not like the others. Its surface is covered in liquid hydrocarbons, lakes of methane, rivers of ethane, rain made of organic molecules. If you stood on Titan, you'd see orange skies, hazy with nitrogen and methane. You'd see lakes bigger than the Great Lakes, filled with liquid natural gas at negative 290 degrees. But dig down, through the ice, through the frozen crust, and there's water. A subsurface ocean mixed with ammonia, acting as antifreeze. Life as we know it can't survive in liquid methane, but life as we don't know it? Maybe. And if there's a water ocean below, that's another habitat. Titan might have two biospheres, one in the methane seas, one in the hidden ocean, both completely alien. These aren't just moons, they're worlds, complex, dynamic, with oceans larger than Earth's, and we've barely scratched the surface. We've sent one probe through Enceladus's plumes. One. We've flown by Europa a handful of times, never landed, never drilled through the ice. We don't know what's down there. But the fact that these moons exist, that they have so much water, changes everything. Water isn't rare. Earth isn't special. We're just one of many water worlds, and most of the water in the solar system isn't on Earth. It's out there, hidden under ice, locked in rock, waiting to be explored. Here's the big question. If water is this common, why don't we see life everywhere? Earth has oceans. Mars used to have oceans. Europa has an ocean twice the size of Earth's. Enceladus, Titan, Ganymede, Callisto, all water. Yet we found life in exactly one place, here. Why? The answer might be that we haven't looked hard enough. Or it might be that water isn't enough. Life needs more than liquid water. It needs energy. On Earth, most life depends on the sun. Plants photosynthesize. Animals eat plants. Everything runs on solar energy trickling down the food chain. But in the oceans of Europa and Enceladus, there's no sunlight. The ice is miles thick. Nothing gets through. So where does energy come from? Hydrothermal vents. Cracks in the ocean floor where hot water, rich in minerals, spews out. On Earth, entire ecosystems thrive around these vents. Tube worms, crabs, bacteria that eat sulfur and methane instead of sugar. They don't need sunlight. They run on chemistry. If Europa and Enceladus have hydrothermal vents, and we think they do, life could exist there. Thriving in the dark, eating chemicals, never seeing a star. But there's another requirement: time. Life on Earth took hundreds of millions of years to evolve, maybe billions. Europa's ocean might be ancient, stable for billions of years, or it might be young, freezing and thawing as Jupiter's orbit shifts. If the ocean keeps freezing solid, life doesn't have time to get started. We don't know how long these oceans have existed. We don't know if they're stable. That's what missions like Europa Clipper will tell us. Then there's the phosphorus problem. Life on Earth needs 6 elements: carbon, hydrogen, nitrogen, oxygen, sulfur, phosphorus. CHOPS. The first 5 are common. Carbon and oxygen are everywhere. Hydrogen is the most abundant element in the universe. Nitrogen and sulfur show up in lots of chemistry, but phosphorus, rare. On Earth, it comes from weathering of rocks. Rain falls, acid dissolves phosphate minerals, rivers carry phosphorus to the ocean, plankton absorb it, fish eat plankton, phosphorus moves through the biosphere. But on Europa, there's no rain, no weathering, no obvious source of phosphorus. Without it, life might not be possible. Or it might use something else: arsenic, silicon, chemistry we've never seen. This is the frontier. The question driving planetary science right now: how common is life? Is Earth a fluke? One lucky planet with the right conditions at the right time? Or is life inevitable anywhere there's liquid water and energy? We don't know. But we're about to find out. NASA and ESA are planning missions to these moons: Europa Clipper, JUICE heading to Ganymede, Dragonfly, a drone will fly through Titan's atmosphere in the 2030s, landing in different locations, analyzing chemistry. These missions won't drill through the ice, not yet. But they'll tell us if the conditions for life exist, if there's organic chemistry, if there's energy, if there's complexity. And if the answer is yes, if we find life, even microbial life, in Europa's ocean or Enceladus's vents, everything changes. Because if life started independently in 2 places in the same solar system, then it's probably everywhere. Every star with planets, every planet with water. The universe isn't just full of water. It's full of life. And we're not special. We're just one branch on a cosmic tree that spans the galaxy. Earth has less water than you think. A thin coating on the surface, less than 1% of the planet. Meanwhile, moons across the solar system are drowning in oceans larger than all of Earth's seas combined. Europa, Enceladus, Ganymede, Titan, worlds that make us look dry. And we're just beginning to explore them. The next 20 years will bring missions to these moons, probes that taste their water, drones that fly through their skies. Maybe, just maybe, discoveries that prove we're not alone. Water isn't rare. Life might not be either. We're living in the golden age of planetary exploration, the age when we finally answer the oldest question in history: are we alone? If this video changed how you see Earth's oceans, hit that like button and subscribe to Space and Scale. Next time, we're exploring why NASA stopped exploring the ocean. The reason will shock you. See you there.